Good afternoon, everyone. It's wonderful to be here with you on this occasion. I am Liz McCormick. I'm the Dean for Academic Affairs here at Bowdoin College. And I'm pleased to welcome you to this Common Hour, which is the Karofsky Faculty Encore Lecture. I'm going to tell you a little bit about the Karofsky Family Fund that enables this lecture, and then a little bit of a background on our speaker today, Mike Danahy. The Karofsky Family Fund was established by Paul Karofsky, class of '66, and his brother Peter Karofsky, class of '62, and Paul's son, David Karofsky, who's a class of '93. The three of them founded the fund in memory of their father, David's grandfather, Sidney B. Karofsky. The fund has underwritten the Sidney B. Karofsky Prize for Junior Faculty for many years, and in 2000, the fund added the Common Hour Karofsky Lecture, which we're having today. Remarkably, the Karofsky Faculty Lecturer features a Bowdoin faculty member who has been selected by students, especially with regard to excellent teaching and as a role model for the field. And so it's my pleasure and it's an honor to recognize Michael Danahy, a senior lecturer in chemistry who was selected this year. Michael is a graduate of Bates College, and I understand along with his wife, also an alumnus of Bates College, and he received his PhD in chemistry at Princeton University. He's been teaching at Bowdoin since 2007, and as I mentioned, he has the title of a senior lecturer, and he teaches many different courses in organic chemistry and introductory chemistry, and he has a class that focuses on drugs, poison, and toxins, I hear, and this class is designed to be accessible by all students at the college. And that interest has led him to speak about drug action and abuse to lawyers and judges across the state of Maine. Outside the classroom, he's the faculty advisor to the Chemerling Society, the Student Chemistry Club, and he's the director of the Bowdoin Science Experience Program and a co-leader of the Bowdoin Science Scholars, along with Stephanie Richardson, who's here today. He's also served as the college mentor for the U.S. National Chemistry Olympiad team. He was the 2012 recipient of the college's Karofsky Prize for Excellence in Teaching, and today we get to honor him with this lecture. I understand that Michael loves to expose students to chemistry, the basic molecular structures and reactions, but also he loves animating the chemistry by bringing in real-life examples that students can relate to, that everyone can relate to. So today in his talk, From Color to Caraway to Cooking, Stories and Lessons from Organic Chemistry, we're going to get a chance to see Mike in action. Join me in welcoming him for this lecture.
Thanks, Liz. Yeah, sure. Thanks. All right. Let's see, make sure this all works. Can everyone hear me? All right, good. Okay, so thank you all for coming on this rainy day. And usually when you hear organic chemistry and a title of a talk, usually not a big crowd pleaser, so I'm happy that we have a lot of people here. And thank you, Liz, for that great introduction. It really was humbling when I got the email a couple months ago about being nominated for this, because it came from the students, so it's nice to have something that I love doing, teaching chemistry, being recognized by the students. But when I first thought about what to talk about for this talk, I was like, why would I be nominated for this? And I think what it is that I like making these connections between organic chemistry, something that I think is a misunderstood chemistry or misunderstood science, and people's real lives. So my goal at the end of this talk, my broad goal, is to make you guys love organic chemistry, because I love organic chemistry, I love teaching organic chemistry, and I love telling other people about it. So that's my broad goal, and we'll talk about some specifics in a sec. Okay? So we got to first think about what organic chemistry is. And organic chemistry starts from really the bifurcation in chemistry. The organic division, life, living things, and the inorganic division, dead things over here, okay? And that really was the historical basis or the historical break in chemistry 150 years ago. But really it's morphed more into the chemistry of basically essentially one element on the periodic table, carbon. Okay, now there's some other ones too, right? I talk about hydrogen every now and then, some nitrogen and some oxygen. But really, I only have 4 elements to be talking about in 2 semesters, right? I have a colleague, Jeff Nagel, who has to basically do all 108 other ones, or I can't do the math, but 104 other ones in 1 semester. But the reason why the reason why carbon is so central to life, whoops, sorry, let's go back, is so central to life, it's where it is on the periodic table. Right, it's really in a sweet spot on the periodic table. If you just count over, there's 8 large columns on the periodic table. It really is in column number 4, right in the middle, kind of east to west on the periodic table. It makes really nice bonds with a lot of other elements. If you go over here, lithium, beryllium, sodium, these are kind of one-trick ponies. Yeah, they make cations, great, that's about all they do. These babies over here, halogens, same deal, they just go the other way. Noble gases do nothing. Broad strokes. But it's also in a nice position kind of north to south on the periodic table. Carbon, unlike its doppelganger silicon, is actually can form three different phases, at least on Earth, right? You can have gaseous carbon, right, carbon dioxide, you can have liquid carbon, think about gasoline, and you can have solid carbon, like sugar cubes or something like that. Silicon, tends to only make solids, right? Sand. That's pretty much all silicon is doing under normal conditions here. Now, there are some esoteric silicon compounds, but by and large, it's only doing one thing. Chemistry is in this nice sweet spot, okay? But carbon, if that was it wouldn't be very interesting, because many people think of organic chemistry as something like this, right? This litany of reactions and functional groups. Here's all the reactions alcohols can do, right? Just this big litany, not very interesting. And if it was just this wouldn't get me going really on chemistry. And it actually didn't get the founder of organic chemistry really that interested either. This is Friedrich Wöhler, who's thought of as, at least, if not the father, one of the fathers of organic chemistry, synthesized the first organic molecule in the lab. And here's what he says about organic chemistry. It's enough to drive me mad. It's a boundless thicket, no way to escape, and one is to dread to enter. He didn't like it, right? And he's the father of it. So what gets me going? Well, I use a quote from my chemical hero, a guy named Robert Woodward, right? If you've taken a class with me, I see a lot of my students out there. You guys have heard about this guy many, many times. And I like organic chemistry from 2 broad reasons. One is from this quote right here, which is basically talking about the utility of organic chemistry, right? Woodward says that we are medicinal chemistry because of organic chemistry. We are clothed because of organic chemistry. We're ornamented, we're protected from it because of organic chemistry. Right? And so if you look at our normal everyday lives, all of these topics and many more have at least a connection to organic chemistry. But it's not just the utility of chemistry, of organic chemistry, that gets me going. It's something more visceral, more, I use the word sexy a lot in my classes, right? Because there's something that gets you going about chemistry. And I go back to Woodward, and Woodward says something more about it. He goes, why didn't I become a mathematician? Apparently he was very good at math. He goes, I like chemistry because I like the crystals, their forms, their formation, the liquids, the distilling, the sloshing, the fumes, the odors, right? There's something really cool about being in the chemistry lab. And if you look at what happens in a chem lab, in an orgo lab especially, you get some really cool things, right? Here's the crystallization of a compound. Here's the separation of an organic phase in an aqueous phase. We play with cool glassware, right, being run under inner atmospheres, right? There's something really interesting about it. And so what I'm trying to get to my students to walk away with appreciation of is not just the carbons and the reactions and that kinds of stuff, but it's this. It's the sexiness, it's the coolness, it's the connections of chemistry, right? Eric Gaze over in the CLT uses this quote a lot in a lot of his talks, just talking about education in general. What are we trying to do, right? And he says that, it's a Yeats quote, but Eric uses it quite often. He says that, Yeats says that education is not the filling of a pail, but the lighting of a fire. Right? I'm not just trying to throw reactions in my student's head, memorize this, memorize this, memorize this, right? I can't. It's way too vast to teach someone all of organic chemistry. It takes years to do this. But what we can do is light a fire in a student so that they'll want to learn more, they'll want to educate themselves on chemistry. And the way I like to do that is by telling stories, right? And trying to connect chemistry to people's everyday lives. So the poet Muriel Rukeyser has a quote that I don't completely agree with, but I agree with part of her sentiment, is that the universe is not made is made of stories and not atoms, right? I don't agree with that second part because it is made of atoms, obviously. But it's without the stories, without the connectivity, right? Science is pretty cold and pretty dead. So my goal today is to make you love organic chemistry, but doing so through some stories. And then hopefully we'll get some lessons about chemistry and also some lessons that perhaps are broader than just chemistry. So the first story I want to talk to you guys about is I've entitled an English proverb of invention. Necessity is the mother of invention. Okay? So we got to go back in time to where organic chemistry really started. I know I talked about Voller, but we're going to kind of fast forward maybe 20 years. And organic chemistry really gets its start in the synthesis of this molecule right here. This is called quinine. It's a really cool molecule. If you've ever had a gin and tonic, right, this is the stuff that makes the tonic water nice and bitter. Also fluoresces under light, which is also cool. It's a natural product that is isolated from the cinchona tree right here, which is indigenous to South America. And the reason why this molecule is important is because quinine was really one of the first anti-malarial agents back in the 1850s. Right, so you can imagine that empires are spreading throughout the world, spreading disease and pestilence and all that kinds of stuff, and you need something to fight the malaria, right? Quinine is it. But we can't just deforest all of South America, and if you're some countries that don't have possessions in South America, how are you going to get your quinine? Okay. So around this time, what was really coming on the scene was this stuff, coal tar. Right? This is the 1850s, 1860s. People are starting to burn coal gas, get petroleum products. People started looking at this coal tar stuff and being able to transform this, which is essentially just carbon and other organic material, into larger, more interesting molecules. So a guy named, Hoffman says, okay, he goes, I can take something from my coal tar, something that's known to exist in coal tar. This is called allyl-toluidine. And he says that, well, this has got 10 carbons. If I take 2 of these molecules, I can make quinine, because quinine's got 20 carbons. And this molecule's got, 1 nitrogen. If I take 2 of them, quinine's got 2 nitrogens. So we took this very arithmetic approach that said, hey, if I could just throw some of these together with some oxygens, I'll get quinine. Now, of course, he didn't do it. He had his student do it. He said, okay, now you go do this. A guy named William Perkin. So Perkin did it. And didn't get quinine, right? The reaction failed, not uncommon. But what he did was he just got a solid brown mess, right? Just garbage at the end of his, at the bottom of his flask. Now, if it was me, I would have been like, okay, it didn't work. Go back to your PI and say, what's going on? But he came up and said, well, let's try something different. He said, maybe this could be a test for molecules that have a nitrogen and a benzene ring in it. A molecule called aniline would fit the bill. And he thought, maybe if I, this would be a nice test that anytime I have a molecule with a benzene ring and a nitrogen and I get a solid brown mess, it's like a test for that molecule. So he said, let's try it with a simpler molecule called aniline and see if I get the same solid brown mess. Does it again, puts his things together, and he gets this molecule instead. Doesn't get the solid brown mess. He gets this. Oops, come on, let's go back. He gets this guy right here. Now, it was black on the bottom of his flask, but when he rinsed his flask with ethanol just to rinse the glassware, what he got was a beautiful molecule called mauvine, right? And I put it here in purple because guess what color this molecule was? Purple, right? A nice purple molecule. And he was pretty excited about it, right? He says, in this instance, the black precipitate was obtained. Upon examination, was found to contain the coloring matter, aniline purple or mauve. And now, why is this exciting? Why is this groundbreaking? Well, it turns out that mauve is the first, or was the first, synthetic dye ever synthesized, right? Beforehand, we were relying on natural sources. And this started the mauve craze in about the 1860s, 1870s. So here's a piece of silk that is colored by Perkins mauve. It got really popular when this lady started wearing a lot of purple. People want to look like her, so mauve takes off. And like I said, it really starts the dye industry, really starts organic chemistry. It was so popular and such a seminal event that even a couple years ago, Google took it up and put it as one of their, I forgot what these things are called, but the things that's on top of the search bar, right? So here we have, before Perkin, we're living in Drab City, right? And Perkin, here he is, makes everything so beautiful, right? A nice synthetic dye. And like I said, before this, we were reliant on natural sources for dyes. Here are some dye molecules right here. Carminic acid right here is isolated from a little buggy that is feeding on cacti, right? So you have to harvest all of these bugs and extract the carminic acid. We have this molecule called, this molecule right here called indigo, right, which is from a plant that's growing in India at the time, right, the indigo plant. And then this molecule right here called dibromo-indigo is from the mucus of a mollusk, okay? Very hard to turn this into dibromo-indigo, but you can do it, okay? And now these colors were used, and so the carminic acid is what makes a nice red of the British redcoats. The indigo made a nice blue color and was used as the royal color back in France. And then dibromo-indigo from these mollusks was known as Tyrian or Tyrian purple, which was used as the purple coloring in tunics of Roman emperors. Okay? So what you can see here is that before Perkin, colors, or at least cool colors, was really a thing for the rich, right? You had to harvest all of these material. They're pretty scarce. You had to process them into color. That's hard to do. All of this takes money, so only the rich had this. What Perkin was able to do was that he was able to open up colors to the masses, right? So nowadays, because of aniline purple and because of all of the different derivatives of that, we now have a lot of different other artificial colors. Right, this molecule right here is brilliant blue, right? Just a lot more of anilines thrown together. This is what makes our blues of M&Ms, for instance. This molecule right here is tartrazine. This is what, if you're like me and like Mountain Dew, this is yellow number 5, a nice synthetic dye. This guy right down here is red number 40, which is used as a food coloring, although there are some bad effects of red number 40, but it's also used in the cosmetics industry. And then this molecule, Procyon red, is used as a fabric dye. So if you're ever wearing red tie-dye, you know where it comes from, right? So now what Perkin did was, through a kind of chance or accident reaction, really opened up the world to color and started the organic chemistry, we'll say, industry. And it really was an industry. If we look up here, I don't know if you can read this, these are 2 ads from the 1800s from companies that are making dyes. So this is the Fabian von Friedrich Baer and Company, and this is the, my German's horrible, the Badische Aniline und Soda Fabrik, right? So here is a red dye, whoops, let's go back, stop it. This is not my pointer, so that's why I'm not really good at it. This is a red dye made by Baer. This is a blue dye made by this company. Cool. Turns out that this company right here, started by Friedrich Baer, if you saw it earlier, turned into the pharmaceutical company Bayer, right? It's a direct correlation. Basically, the dye industry, the market got saturated by all these dye companies starting up. So Friedrich Baer goes into the pharmaceutical business, makes aspirin. And then this company down here, this Badische Anile and Soda Fabrik, turns into the company BASF. And BASF, if you're not a chemist, it might not seem that applicable to you, but it is basically the largest chemical company in the world, BASF. So really, like I said, starting with color, we've opened up organic chemistry and really brought some good things to life, I guess. Other aspects that have come out of aniline and Perkin's discovery, again, we were looking at this molecule, aniline, which was the root cause of all of this. Aniline has 2 direct descendants. Aniline can be turned into these 2 molecules right here. This is called Prontosil, which is a sulfa drug, and sulfa drugs were the first antibiotics on the market back in the 1930s. You can kind of see, the benzene ring plus the nitrogen. Winston Churchill had a bad strep infection in the 30s, was cured because of a sulfa drug. Franklin Roosevelt's son, again, another strep infection, cured by a sulfa drug. This molecule over here, another aniline derivative. Again, you can see the ring and the nitrogen. This molecule right here is acetaminophen or Tylenol, right? So again, a chance experiment getting us some things for our normal lives. Also some humorous side to this story I always love. There's a molecule out there called phenolphthalein, And phenolphthalein is not an aniline derivative, but is a phenol derivative. So these are benzene rings, but instead of having a nitrogen here, we have a oxygen. And this molecule, it turns out, was developed as a dye and makes a cool red color. Fabulous. We use it as for chemistry demonstrations, for the water into wine demonstration. So if you can turn a clear solution a beautiful wine color. This actually has a direct applicability to our lives. Phenolphthalein, since it was a red dye, was actually used about 100 years ago in Hungary. So Hungary was known for red wine. Around 1910, I believe, the red wine crop failed. They had to import white wine, but Hungarians like red wine. So what do you put in your white wine? You put in your phenolphthalein. Okay, great. You got your red wine. But what actually happened was there was a massive, I'll just say, a massive diarrhea outbreak in Hungary at the time. Turns out that phenolphthalein, a great colorant, we used it all the time in the intro lab as acid-base indicator. It also turns out to be a nice laxative as well. So X-Lax, so here's a nice box of X-Lax. I think from the 80s, if you can read it right down there, is a phenolphthalein laxative, okay? So why am I telling you this? Yeah, they're kind of cool stories. But the lesson from this story, I think, is I'm taking it from a quote from a Walpole poem called The Three Princes of Serendip. And this poem is where we get the term serendipitous or serendipity. And the quote that I like from this poem, it says that they were always making discoveries by accidents and by sagacity of not the things they were in quest of. And that's what happened with Perkins, right? Perkin started by an accident, mixed the things together, got a brown mess. But he had sagacity, right? He had insight, he had knowledge, he had an intellect to take that accident and to turn it into something useful, right? Which then we're now using and we're still the recipients of today, okay? The second story I wanted to tell you guys about is, I'm entitling it Through the Looking Glass and What Alice Found There. So this is the title of, obviously, the Lewis Carroll book from the 1800s. And if you've had chemistry, you probably know where I'm going, but we'll start from the very beginning. So people have noticed that, and if you guys have ever had a wine cork, sometimes you'll see a solid sitting on the inside of a wine cork. That solid right there, people have called wine diamonds. And what they are is they're salts of something called tartaric acid. And people didn't know what tartaric acid looked like. They just knew that, okay, there's the chemical formula, right? It's got carbons, hydrogens, and an oxygen. Okay. People were looking a little bit further into wine and trying to pull other stuff out of it. Actually, I should back up. This molecule, when they analyzed it, did something called rotating plane polarized light. So what does that mean? Well, it turns out that this molecule, if you put in something called a polarimeter, and what a polarimeter is that you have a nice light source right here. And what happens with the light source is that light comes out in all directions. So you pass that light source through a polarizer, kind of like if you ever have polarized glasses, they work on the same idea. And so the light, which was coming out in all directions, will now come out in one plane. This is called plane polarized light. And if you take that plane polarized light and pass it through a sample of your molecule, like tartaric acid, what happens at the end is that if you put your eyeball out here, what you see is that light has been rotated. So what was coming out in this plane has now been rotated to the left or to the right. So people notice that the tartaric acid from wine diamonds rotated plane polarized light. Okay, cool, fabulous, who cares? Well, they dug into some more things into that wine bottle. They looked at something called para-tartaric acid, or para-tartrate, which is found in wine, but also you can make it synthetically. It turns out that para-tartaric acid, or para-tartrate, has the exact same chemical formula as tartaric acid, behaves exactly the same chemically as tartaric acid, but the rub is that it doesn't rotate plane polarized light. So people were trying to figure out what is going on here. So one flavor of tartaric acid rotates plane polarized light, one flavor doesn't. What the heck's going on? Well, French guy, Louis Pasteur, takes a look at this. So Pasteur, I think most people are comfortable with Pasteur, pasteurization, microbes, all that kinds of stuff. But his real mark, at least for chemistry, was on his work of these rotating plane polarized light. What he did is that he took some salts of tartaric acid and para-tartaric acid and crystallized them into little crystals, right? And they're quite small, so he had to look through his magnifying glass, and he just looked at the crystals and see what they look like. What he noticed here was that the tartaric acid, the stuff from the wine diamonds, there was only one type of crystal. And this is based on a drawing of what Pasteur saw in his microscope, right? So just the shape isn't important to us right now, but just there's the shape of the crystal, okay? And he noticed that, again, when he put his wine diamond into the water and passed it through his polarimeter, it rotated light to the right. Now, we did the same thing with the para-tartaric acid, the para-tartrate, okay? And he noticed that there were two crystal types there. One that looked like this, one that looked like this. This one, if he took it out with his tweezers and put it in his polarimeter, that rotated light to the left. This one, if he took it out with his tweezers, rotated light to the right. Now, this is a really arduous thing to do, right? You can imagine sitting there and pulling little crystals out, but he did it, right? To actually show himself that you could make light that rotates to the left and rotates to the right. And the reason why a para-tartaric acid didn't rotate any light itself on its own was because it's a mixture of the left and the right. So if you sum together left and right, the net rotation is going to be 0. But the big thing that he noticed here was that these two crystals, although being very cool looking, were mirror images of each other, right? So they behaved exactly the same, except this whole plane polarized light business, because they are mirror images. This is something called chirality in organic chemistry. And we see chirality all the time in our everyday lives, right? These are things that are the same but not the same, okay? This led people to start thinking that, well, the crystals themselves are different, or the crystals themselves here are mirror images. The molecules themselves are going to be mirror images. So it turns out that the wine diamonds have one crystal type. Turns out they also have one molecule type. There it is, right? So these little wedges are showing these bonds are coming out at you. It turns out that the para-tartaric acid has two crystal types, two molecule types, and those molecules are mirror images of one another. Again, same chemically, but not the same in terms of the way that they rotate plane polarized light. Same, but not the same. So where am I going with this? Well, like I said before, we see this idea all the times in our normal lives. Our hands are mirror images of one another. Are they the same? Is your left hand the same as your right hand? Kinda, right? I mean, they're largely the same, right? I mean, I got a thumb and 4 fingers, a thumb and 4 fingers. But your left hand can't do what your right hand can do, and vice versa, right? They're mirror images of one another. Turns out molecules are the same way. Okay? There's other examples of this whole chirality, this handedness. Here are two shells, right? Here's kind of like, I guess, a left-handed shell and a right-handed shell, right? They're mirror images. They're not exactly the same. Here's DNA. It turns out DNA has a left-handed way of doing business and a right-handed way of doing business. And it turns out they're not the same. They're very similar, but not exactly the same. Okay? And so with this, how this manifests itself in our normal lives is, with one example would be with a molecule of this. This is called carvone. Hopefully you can see here that these molecules are mirror images of one another. Is that correct? Okay, right? These are mirror images. Like, so if you would imagine that there was a mirror plane running down the middle. These two molecules are largely the same. They have all the same chemical properties, the same melting points, boiling points. They react the same. But they differ in the way that they rotate plane polarized light. They also differ in their scents. It turns out that we'll call this guy the left-handed carvone. This smells like spearmint. So if you were to open up a bottle of carvone, the left-hand carvone, and take a sniff, you'd smell spearmint. If you were to do the same thing with this right-handed carvone, you don't smell spearmint, you smell caraway, so pickles or rye bread. And so the question is why, right? Why is it that molecules that are pretty much identical, right? Left-handed, right-handed, why are they so acting so differently? Well, it turns out it's because that these molecules are handedness. There are items in our body that are handedness, or that are handed. So in order for these molecules to elicit a scent in our body, we have to have those molecules fit into receptors in our nose, okay? So you can imagine this, and I'm going to do it, but you can imagine that, and you guys can do this too. Here's my receptor, right? I have a right-handed receptor in my nose, right? I have two flavors of carvone, right? I have right-handed carvone and left-handed, right-footed carvone and left-footed carvone. If I try to fit things into my receptor, my right-footed carvone fits in nicely, right? Maybe that's what Caraway smells like. Is my left-footed carvone going to fit into my shoe nicely? No, right? Just try it, right? You're going to be really jamming your foot in there. This is exactly what's happening on the biological level, right? The receptor that the carvone needs to bind into is kind of like my right shoe, right? And the two carvones, because they're mirror images, my right foot can't fit in, will fit nicely into my right shoe. My left foot doesn't fit so nicely into my left shoe, into my right shoe. Now, you might say, all right, that's great, just sense, who cares, right? I don't really care about that. It turns out that this has a bigger effect for things like pharmaceuticals. So this is a molecule called penicillamine. It turns out that there are two flavors of penicillamine. We'll call them left-handed and right-handed penicillamine. The left-handed one is an effective treatment of Wilson's disease, so kind of rheumatoid arthritis. The other penicillamine, the right-handed one, has severe side effects, right? It's not fitting into receptors the same way. It has a lot of bad effects. A tuberculosis drug, ethambutol, the left-handed one, we'll say, is a suitable tuberculosis treatment, fabulous. The other one causes blindness, makes you blind, right? And so a little bit of mirror imagesness, this chirality, really has some huge effects on the activity of these molecules. The most famous case would be thalidomide from back in the 60s. Turns out that thalidomide has two flavors, right? Again, we'll just call this a left-handed one. This is a potential sedative, so it was given to women who were pregnant to stave off morning sickness. The other one causes birth defects. So since the women were given both so-called enantiomers, or both flavors of the molecule, many children were born, in Europe at least, with something called phocomelia, which is a reduction of limb sizes, that kinds of stuff. Never really made it into the United States beyond clinical trials because of one of the good stories of what the FDA can do. So this woman right here, Frances Kelsey, who just died a couple of years ago, she was the person at the Food and Drug Administration who basically kept asking the company in Europe that was pumping out thalidomide for more data as to how it works. Is it going to do anything to fetuses? Is it going to do anything to pregnant women? And the chemical company kept coming back saying, yeah, it's fine. It'll work. Don't worry. It's working great over here in Europe. But she kept pressing for more and more data. And by the time the phocomelia came out, she was still pressing and not allowing thalidomide to be approved. So thalidomide largely didn't get released into the U.S. market. So she truly is one of the heroes of chemistry, we'll say. Thalidomide does have a bright side. Because of this phocomelia, what it was found was that the reason why this was causing phocomelia was because it was cutting off blood supply in the fetuses for limb growth. So if you can't have blood going to what's going to potentially be an arm, your arm's not going to grow. So people have been started to use thalidomide derivatives, and here's one of them called Revlimid, as a cancer treatment. So the way that this Revlimid works is by basically cutting off blood supply to cancer tumors and to cancer cells. So like I said, there is a bright side to this nice story, okay? So you might ask yourselves, well, all right, good, bad. We saw two other examples of good and bad. How are we going to make it so that we only get the good and not get the bad? Right? So a lot of work has been done into something called chiral catalysts. And the way a chiral catalyst works is basically the same way that you would make a glove. A glove comes in a left-handed form and a right-handed form. If you want to make only a left-handed glove, which is this right here, right, you need a mold for that glove, right? So you could imagine that I have my mold, my material would go in, and anything that comes out is going to be left-handed material, right? So a chiral catalyst is basically a mold so that we only make one of the two hands of that molecule, okay? And so people have made these chiral catalysts for many different applications. The two that I'll show you about are the synthesis of something called L-DOPA, and L-DOPA is essentially dopamine, so this is used in Parkinson's treatment, and L-DOPA has a carbon right here that can have a left-handedness or a right-handedness. Only one of them is going to be effective for treating Parkinson's. So Knowles made up a catalyst, a rhodium catalyst right here, so that in this key step of the reaction, where this double bond gets turned into this group right here, only this handedness of the molecule is made. You only make this, which then goes on to L-DOPA. And here's his chiral catalyst. Here's his mold. Here's his left glove. So when the molecules go in there, we're only making one product. Okay? Also, Nayori has a catalyst where he starts off with a molecule called myrcene, and through a number of steps makes menthol right here. And now you might be asking yourself, all right, who cares about menthol? But menthol is, made on the train car loads full every year, right? Menthol is in aftershaves, it's in scents and perfumes, in cigarettes even, right? This stuff is pumped out a lot. It's a natural product, but you don't want to harvest it all from natural products because it would take forever. So we have this chemical process to make it. But Nayori developed a catalyst, a chiral catalyst, so that at this step right here, we take that double bond and only get this handedness of that carbon right here, which then goes on to make menthol. Okay? Nayori and Knowles got the Nobel Prize for this back in 2001 when I was in graduate school. Right here's Knowles' diploma and Nayori's diploma. And the reason why I like to show this is because I guess the Nobel Prize Committee does have a sense of humor, right? Because it has the nice shells right here, the handedness of the two molecules. Okay? So what's my lesson for this story? Why would I tell you about this? Well, if we go back to Alice in Alice in Wonderland, she says here a great quote, "Perhaps looking glass milk isn't good to drink." Right? If you go through the looking glass, you're going to be in the land of left-handedness if you were originally in the world of right-handedness. Things in this land aren't going to fit the same way in your receptors as things did in this land. I'm not picking on left-handed people, but whatever. Right? So we have to think about that small change had a huge difference in the way those molecules react. But a nicer lesson from this story actually comes from what Biot, who was an old French chemist, told Pasteur when he looked through the microscope after Pasteur made his discovery. Biot says, "My dear child, I've loved science so much that throughout my life that this makes my heart throb." And this really is why chemistry in general, organic chemistry, and actually chirality for a weird thing actually gets me going. It's a different way of thinking about the world. And once you kind of know about chirality, you actually look at the world a lot differently. Everything becomes handedness, right? You're looking for left-handed things, right-handed things all over the place. And this really, as I just told my class today, chirality is one of the big ideas from first semester organic chemistry. It's one of the first big ideas that really is unique to organic chemistry, this handedness of the world. Okay. The last story I wanted to tell you guys about is I'm entitled and called The Joy of Cooking, right, which was the title of a book which has been published for about 80 years now. And why am I talking about cooking? Well, basically because my boss, when I was in grad school, every time he came into the lab, he wouldn't say, "How's it going? How are you?" He would say, "How's cooking, Michael?" Right, because we were synthesizing molecules, all that kinds of stuff. So I always open up with this in my intro chemistry class as to what does a chemist look like? And most people think that, we wear lab coats and we're working in front of fume hoods and blah, 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 which is true. But I always tell my class, this guy right here, he is a chemist, right? He's got his lab coat, I guess, right? He's got specialized glassware, or at least metalware. He's got a heat source, right? Here's his little hot plate. We would use hot plates. He's using something a little bit differently. But he's a chemist, right? So obviously this is Wolfgang Puck, and he comes out with a great quote. He says, "The reason why I like cooking is because it's like painting or it's like a song, right? I have just as only a certain number of notes or colors to paint or to write a song with. I only have a certain amount of flavors to make my compounds, to make my meals. But it's how you put the flavors together which make for a great meal." Organic chemistry, or chemistry in general, is the same way. As remember, I've only got a few ingredients to stick together, right? I'm only responsible for 4 atoms on the periodic table. But it's the way these atoms are put together that really makes cool molecules, interesting molecules, useful molecules. Okay? Now, synthesis, or making molecules, really starts off with this guy again. This was Wohler, like I said, the guy who started organic chemistry. Back in the 1830s, he was basically trying to do a kind of esoteric reaction of trying to turn silver isocyanate into ammonium cyanate. Great. Turns out that when he tried this reaction, he did not isolate ammonium cyanate. What he isolated was this molecule right here called urea. And you're like, okay, why do we care about this? It turns out that urea is an organic molecule, right? It's in urine. It's a byproduct of metabolism. And this was the first synthesis of an organic molecule, a molecule that came from a living thing out of things that did not originate from living things, right? Up until this point, people had thought about this idea of something called vitalism, that only molecules that come from living things can be made by living things, right? So I can only make urea if my dog has an accident or something like that, right? I can't make it in the lab. Wohler started to basically chip away at that idea. He got really excited about it. He said, I can no longer hold my chemical water. I must tell you that I can make a urea without the use of kidneys of any animal, be it man or dog, okay? So the first synthesis, but like I said, not a very interesting synthesis. Urea is not a molecule that gets an organic chemist really going. So just like there's cooking and there's cooking, right? There's synthesis and there's synthesis. So the story I'll tell you about synthesis is this molecule right here, which is called tropinone, which is a really cool molecule. If you make a model of it, it's polycyclic. It's got like a 7-membered ring with like a little tent of a nitrogen. It's great. It's fabulous. Turns out that tropinone is important. We need tropinone because of what we can turn it into. Whoops. We can turn it into this baby right here, which is called atropine, which is an important pharmaceutical. The World Health Organization says that it's one of the top 100 drugs that a country has to have to be considered having a modern medical facility. And also, it's the important part of a molecule called cocaine. And I'm showing cocaine up there not just because of its addictive properties, but cocaine is important as an anesthetic. It's a good topical anesthetic. And a lot of anesthetics that are based off of cocaine have been produced afterwards, but they are not horribly addictive. Okay? So atropine needed to be made at around 1917 because of World War I. Atropine is really good because it can counter your heart stopping, your heart slowing down. It can also is a good antidote for poisons. So you can imagine in 1917, people are lobbing gases left and right at each other. Atropine is a nice antidote to those poisons. So people started to try to make this stuff. So again, here's tropinone. One of the first syntheses that predates World War I is the so-called Vilshire synthesis. It's one of these seminal events in organic chemistry. So he takes this ring compound right here and just goes, this ring compound right here and goes all the way down to there. Not a very sexy synthesis. He only gets about 0.5 to 1% yield. So if I need this to cure my poisons or to start people's hearts, this ain't a way of doing it. Well, around 1917, a guy named Robinson comes along, and through 2 starting materials, essentially 1 step, he makes tropinone. Okay? And he makes it in really good yield. If you just kind of tweak this reaction a little bit, you can get a reaction that works out to be about 90% yield. So Robinson really got it right with this synthesis, A, because he's making a lot of the material, and B, because it's starting from material that's very easy to begin with, right? So these 2 are available from natural products. But it also brings up an idea of why is this synthesis better than this synthesis? And it's something to do with the chemists throw a lot around the world of the idea of elegance, right? This is not an elegant synthesis. I'm trying to go from here to here through something like 20 steps. Not very elegant. This is an elegant synthesis, right? 3 materials being thrown together to make a rather complex molecule in high yield. And if we remember, not remember, but if we know what Leonardo da Vinci said, simplicity is the ultimate of sophistication, right? This is elegant because of its simplicity, okay? I was on a committee a number of years ago, and someone who was not a chemist, I had mentioned in this committee meeting that, that there's an elegance to chemistry, there's an elegance to molecules, and this person looked at me with disdain as to, like, elegant? How can chemistry be elegant? This is how chemistry is elegant, right? Three simple molecules turning into a larger molecule, okay? Now, synthesis has developed a lot since then. If we go to my chemical hero, a guy named Woodward again, he basically says that trying to synthesize the molecules that occur in nature is one of the most satisfying items in chemistry. And he should know, he has synthesized a ton of molecules. I don't know if you guys can see this, but he has synthesized in the lab chlorophyll, which is obviously found in leaves. He has synthesized vitamin B12, a huge molecule. He has synthesized quinine, our original molecule that Perkin was trying to do. He's synthesized cholesterol and tons of other molecules, right? He really is one of the greatest, organic chemists out there. But I don't want to talk about one of these molecules. I want to talk about synthesizing a different molecule, one that, that Woodward did not synthesize. And we're going to talk about this molecule, a molecule called Taxol, right here. Taxol is a molecule that's isolated from the Pacific yew tree, from the bark of this beautiful tree. It grows in the rainforests of the Pacific Northwest. And it was found to be, in the 1970s, a potent chemotherapy agent, which is really great. And the way it actually kills cancer cells is by a mechanism that was basically a mechanism that had no other drugs on the market at the time, right? So this killed things in a totally new way. So you can imagine if you use this drug in concert with some other medications, you could really give cancer, a 1-2 punch, okay? The problem with Taxol is that you need to take about 20,000 pounds of bark from these trees to make 1 pound of Taxol, which is not very good, right? The other bad thing about this is that this Pacific yew tree is one of the slowest growing trees out there. These things grow to this height, is about a 100-year-old tree, right? So you can imagine that unless you want to deforest the entire Pacific Northwest, you ain't going to get much Taxol, okay? Well, what are we going to do? We can't take this all from trees. We're going to try to make it. So it turns out in 1994, right up here, right, 1994, and if you look at the date, February 17th, 1994, so we're at the 25th anniversary of the total synthesis of Taxol, right? It was really a seminal event because it's a really complex molecule. There was competition amongst organic chemists to be the first one to synthesize it, and a group out in Scripps synthesized the molecule. And so the way that they did it right here is, here's our Taxol up here. Basically, the group took 3 precursors. They synthesized this bit, synthesized this bit, synthesized this bit, and then made the molecule of Taxol. Now, that's all well and good, but it took 28 chemical steps, and this is from the article in Nature. It says that it takes 28 chemical steps, and based on these 2 intermediates, which also have to be prepared, so the synthesis can hardly be described as commercially viable, right? So this is not going to be a good way of making Taxol. But we shouldn't forget about it, because it says it would be wrong to underestimate the importance of this elegant synthesis, again, that word elegance, to make Taxol. So how are we going to get Taxol? Well, the story of Taxol is really cool because it turns out that this tree right here, this is the Eurasian yew tree. These grow super fast. You might have one in your front yard. These are the source of this molecule right here, right? This polycyclic molecule, which through a hop, a skip, and a jump can be taken to Taxol in about 80% yield. This tree grows really fast. All we need to do is just harvest its leaves. We don't need to kill it, right? So now there's fields of these yew trees being produced or being grown just for the production of Taxol. So the story of Taxol is nice because not only is it cool synthesis, but it's a nice intersection between pure chemical synthesis and biochemistry as well. But synthesis is not just all about utility, right? It's not just making things that are useful to help us out. There's also some beauty in some synthesis, right? Why did somebody paint this? Why did somebody write this, right? This is The Marriage of Figaro by Mozart. They did it not because they don't have any implicit utility. They did it because it's beautiful to do that. This is beautiful. That's beautiful. Synthesis and molecules can be beautiful too. I have a couple of examples for you. Molecules called fullerenes, really cool molecules. This is basically a ball made out of carbons. It's a soccer ball made out of carbons. It's a really sexy molecule. It's really elegant. I mean, it's perfectly symmetric, and it's a great molecule. They're named fullerenes because of this guy right here. This is called Buckminster Fuller, who was an architect who made these geodesic domes, so you can see why they would call them this. But it would be cool just to make this molecule, just because we can, just because someone made, just like someone painted Mona Lisa and someone writes music. And it turns out that fullerenes have been synthesized. Here is a rational chemical synthesis of C60 of a fullerene, right? It's actually a very few number of steps to take me to intermediate called 2. Here is intermediate 2, and the real cool part about this synthesis is that they throw it and do, basically just throw it into a really hot oven, 1100 degrees, and 10 bonds are made at once. You take this flat molecule, cook it up, and you make your soccer ball. Pretty cool, pretty elegant to make not only an elegant molecule, but an elegant synthesis as well. There's tons of other examples. I know I'm running out of time, but this is the problem when you get someone to ask someone to talk about what they're passionate in, you start running over on time. One that was recently out in C&E News was that chemists tie the most complex molecular knot to date. Right? So this is a molecule of basically huge strands of carbons that are all knotted together beautifully. So it's a knot that's on the order of microns or nanometers across, but it's a knotted molecule. So here's what it looks like. Here's a picture of how they did it. They basically started off with these little strings tied around some metal atoms, and then doing something called a ring closing metathesis. They were able to close the ends of the strings to make this loop tied into this loop, tied into this loop. Why would you do that? Because it's cool. And the last one that I usually show my class is that chemists can also make anthropomorphic molecules that look like people. Right? So here's what the body of the molecule would look like, and you can change its head, right? So you can make the nano pilgrim, the nano green beret, the nano jester, the nano chef, the nano baker, right? Why would you make that molecule? Because you can, because it's cool, right? So, and there was a nice quote from Woodward about synthesis. Why do we synthesize molecules? It might seem like it's totally pointless, right? Not if you're not going to make a molecule for utility. But he says that synthesis is like a mountain that hasn't been climbed, a sea that hasn't been charted, or an untilled field, right? It's because that they're there, because they're challenges for us to make. Now, some of them might be a challenge for utility, practical, but some of them might be a challenge just because they're beautiful molecules. And it's nice to have both. So my last lesson in this last bit is basically based off of this quote. Let's think about making things or having things that were beautiful or useful, right? The practicality of synthesis and the beauty of synthesis as well. Okay? So just in conclusion, what I hope to do in this talk today was at least illuminate you a little bit onto organic chemistry. A, teach you some stuff, right? So we talked about color and what aniline is. Now you guys know what aniline is, right? Talk about handedness of molecules, this idea of chirality, and then synthesizing organic molecules. But there were some broader lessons here, right? There was that serendipity of Perkin's discovery. There was this idea of Pasteur really looking at molecules and noticing those small differences, things were same but not the same. And then making things that are beautiful, that are useful, yes, but also synthesis for its own beauty as well. So that's all I have. I hope that you guys can take away a little bit of why I love organic chemistry, and hopefully I have at least turned you on a little bit into organic as well. So with that, I guess I'll take some questions.
Michael answer some questions?
If you got any.
Enough time for one or two?
Oops, I'll pick that up later. Uh-oh.
So,
Yeah.
I guess you like synthesizing things. So what were you trying to synthesize with your PhD thesis?
Oh, good question. Yeah, so what we were trying to do when I was at Princeton was we were trying to derivatize surfaces of metals. So it was a nice project because it, just like how this talk, I tried to have a lot of threads going everywhere, my PhD research did too. So if you take a piece of titanium for like a hip implant and you try to basically, you know, put it into your hip as is, it'll stay in there, but it's going to rock around after a number of years, and about after 7 to 10 years, you need that piece of titanium to be taken out and a new one put in. And you can imagine that if you got the first one put in at 60, you don't want to go under the knife again at 70 to have another piece of titanium thrown in. So what we were trying to do is we were trying to derivatize the surface of titanium so that you could basically link proteins onto the surface, so that when that titanium goes into your body would recognize it not as a piece of titanium, but it would be coated in proteins. And so your body would say, hey, that looks like me. I'll start growing to it and incorporate it into the body, and so it won't loosen over time. And so we worked a lot with chemists, biologists, and even engineers to figure out how tight that bonding was.
Thank you.
Sure. Thank you. Thank you.